Okay, let's just dive right into this. Welcome to today's Explainer, where we're going to be tackling the fascinating and honestly sometimes absolutely hellish journey of a network packet inside Kubernetes. We're going all the way from the pod down into the guts of the Linux kernel and out to the overlay network. So if you've ever stopped to wonder how your data actually flows when you deploy a cluster, well, you are definitely in the right place. Here's our map for today's descent into the under-the-hood mechanics that are actually powering your clusters. We'll start off by breaking down the core illusion of Kubernetes networking, trace some packets on a single node, bridge that terrifying gap across different nodes, explore the hidden dark world of IP tables, look at how eBPF is totally changing the game, and then wrap up with the real truth about what Kubernetes actually is.
All right, part 1, the illusion of Kubernetes networking. Let's start by shattering a massive illusion that most of us have when we first start learning how K8s operates, because it fundamentally shifts how you need to view your clusters.
Seriously, think about it for a second. When pod A needs to connect to pod B, have you ever stopped to ask where that packet actually goes in the real world? It seems like it should just be a straight line, right? But the reality, well, it involves a crazy labyrinth of VETH pairs, Linux bridges, IP tables, contract, and VXLANs.
Notice the stark contrast here. A lot of people think, wow, Kubernetes is incredibly powerful, so Kubernetes itself must be what's transferring all my packets. And no way, that is completely wrong. Actually, scratch that. It's not just wrong, it's a fundamental misunderstanding. Kubernetes doesn't actually route or switch anything. The true puppet master handling your actual data traffic, that's the underlying Linux kernel.
Instead of switching or routing, Kubernetes is really acting as the ultimate orchestrator. Establishes namespaces, it modifies routing tables, it manipulates IP tables, and it calls on CNI plugins to do the heavy lifting. The real data traffic stays entirely inside the Linux kernel. You can kind of think of Kubernetes simply as a manager manipulating this entire network universe built on top of these core Linux elements.
Moving on to part 2, same node packet flow. With that illusion shattered, let's look at the simplest scenario first. We're going to follow our packet as it travels between two pods living on the exact same physical node.
So when Kubernetes creates a pod, the container runtime builds a Linux network namespace, which means the pod gets its own completely independent network world, right? Complete with its own ETH0, routing table, ARP table, the whole shebang. Now, to connect this isolated world back to the host, a VETH pair is deployed. Think of this VETH pair as an invisible virtual network cable. One end sits inside the pod, and the other just plugs directly into the host node's network namespace.
So the absolutely crucial point here is that when a packet leaves pod A, it drops out of the pod's namespace, travels down that VETH cable, and enters the host. In a same node scenario, it's actually pretty straightforward. The packet crosses a standard Linux bridge, which is usually set up by a CNI plugin like Flannel, Calico, or Weave, often showing up as something like CNI0 or Flannel.1. After it crosses that bridge, the packet goes right up the other VETH cable, and boom, into pod B. It's essentially the classic Docker bridge network concept, just scaled up for Kubernetes.
Okay, part 3, cross-node overlay networks. That covers the simple path. But the tension really rises when our packet has to cross the terrifying void between separate physical nodes. You see, Kubernetes has this really strict rule. Every pod must be able to communicate with every other pod directly. But out in the real world, different nodes often do not reside on the same layer 2 network. So how on earth do we bridge that gap? Well, we rely on an overlay network. And the most common implementation of this is VXLAN. It basically acts as a protective transport vessel, taking your original pod packet and encapsulating it inside a totally separate UDP packet. Let's follow the journey of that encapsulated packet. The original plaintext packet leaves pod A, hits the Linux bridge, and is handed off to a VXLAN device. Right here, it gets wrapped up in that UDP envelope. It then travels out of the physical network interface card, across the literal real-world physical network, and eventually reaches the target node's NIC. Once it arrives safely, the VXLAN is unpacked, the plaintext packet is routed through the local Linux bridge, up the VETH cable, and finally into pod B. It's honestly a massive, beautiful collection of Linux network technologies just working in perfect harmony. Which brings us to part 4, the IP table's dark world. Now we have to descend into what I like to call the dark underbelly of the Linux kernel, to meet the hidden forces secretly controlling your service routing. Brace yourselves for this one, because there is another massive secret a lot of users just don't know.
When you connect to a standard service IP, let's say a plain text cluster IP like 1096.0.10, that static IP doesn't actually exist as a real host machine anywhere in your cluster. I'm serious. It is completely 100% fake. That cluster IP is literally just an IP tables NAT rule. By default, kubeproxy operates in IP tables mode, and to make these service IPs actually function, it generates tens of thousands of these rules. And if you've ever had the misfortune of trying to manually debug an IP tables chain, you know exactly how painful this gets. They just sit there in the background, secretly forwarding your traffic to the actual real pods behind the scenes. But tracking all of this forwarding requires a specific Linux component called contract, and it is a vital, but frankly terrifying piece of the puzzle. Contract records every single connection state, whether that's a SYN, an established connection, or a FIN. Why is it terrifying? Well, because if the contract table blows up and overflows, your entire Kubernetes cluster network can experience instant and catastrophic abnormalities. It is a very real, very dangerous bottleneck for large-scale Kubernetes deployments. Let's turn to part 5. eBPF replaces legacy architecture. Fortunately for all of us, technology has evolved. Let's look at how modern network architecture is finally replacing this fragile legacy bottleneck. Increasingly, modern Kubernetes setups are utilizing eBPF through tools like Cilium. Unlike traditional iPables, which basically forces your packets to linearly traverse massive, slow, sequential rule chains, eBPF completely changes the game. It injects routing programs directly into the Linux kernel itself. You no longer need giant iPables or those traditional kubeproxy components. The packets just skip all that legacy fluff and travel via the kernel fast path, meaning they're routed almost instantly at the absolute lowest level of the operating system. The result? An absolutely enormous performance difference. And that brings us to part 6. K8s is automated Linux. This is the ultimate takeaway, the grand resolution of our packets journey today. The very next time you run a command like Kubernetes apply, I really want you to remember what is actually happening. You aren't merely creating a pod. You are sending instructions that command the Linux kernel to build an entire virtual network world. Kubernetes is simply the high-level controller of that sprawling kernel-level universe.
You know, when you're learning Kubernetes, it's so easy to just focus on YAML files, deployments, and services. But the true core of it all is Linux networking. If you don't grasp namespaces, veth pairs, bridges, routing, IP tables, VXLAN, contract, and eBPF, you'll never fully understand how Kubernetes truly operates, because it is, at its heart, an automated Linux network laboratory.
And that is all we have time for in today's explainer. But don't worry, our journey into the deepest, darkest parts of this automated laboratory is far from over. In our upcoming explainers, we're going to dive into CNI principles, completely tear apart kubeproxy, and compare Cilium's eBPF directly against IP tables. Until then, I want you to ask yourself, when you deploy your next application, are you actually controlling your network, or is Linux secretly running the show behind your back? Stay curious, keep exploring your clusters, and I will see you in the next explainer.